Hi, I'm Mark Weitzman. Welcome back to our topics and problems in theoretical physics and our long problem today on complex analysis. So I've deformed the contour in the previous videos, and we've shown that this part cancels with this part. We're left with these four integrals, I1, I2, I3, and I4. If we evaluate those sum, we'll have our integrals. So let me just write that down. I equals I1 plus I2 plus I3 plus I4. Okay, that's good. Now, before I evaluate all these integrals, I want to evaluate the phase shift for each one. So, for I1, on this segment, as I mentioned earlier, it's the same as the pole, and all the points on this section have the same phase shift, and we're going to get the same e to the 2 pi I over 3 factor. On I2, it's the same thing. If you remember, I said all the poles evaluate to the same thing on the first sheet, and on this whole branch point, as long as we're inside here, it's the same e to the 2 pi I over 3 factor. You can verify this if you want, and I did, doing some maple calculations, but there's also geometric ways of doing it. Now for I3, it's the same thing as we did before. When we're on one of these points, we end up having to rotate by an additional 2 pi. Instead of going from like here to here, we're going like that, so we get an extra 2 pi contribution to this phase thing. So all along here, you can work it out, and you're going to find it's e to the 4 pi I over 3 is the phase shift. And again, as I mentioned, it's continuous. Here, you could see like a lot of it comes right from over there. Before we were going that way, now we're going this way. And on I4, you can think of this as like every time we go on a new sheet, we get our points that are on the branch lines inside the branch points. They get this additional phase shift of e to the 2 pi I over 3. On I4, we also have e to the 4 pi I over 3. Again, I encourage you, if you don't quite understand it, just actually work it out for any point here or any point here or any point here. So, now we can write out our integrals. I don't think I need this anymore. Let's write out our four integrals. I1 is equal to the integral. We go from 1 to 0. We're on this thing. We're going this way. d rho e to the minus 2 pi I over 3 divided by e to the 2 pi I over 3 1 minus rho cubed to the 1/3. Again, we're inside 1 here, so this is the absolute value way of writing it. Minus rho e to the minus 2 pi I over 3. And reversing the order of integrals and doing some cancellation, we're going to get the integral of minus d rho. If I multiply everything by e to the 2 pi I over 3, this becomes 1, this becomes 1, this becomes e to the 4 pi I over 3, but I want to make that with a minus sign, so I'm going to have e to the minus 2 pi I over 3, 1 minus rho cubed to the 1/3 minus rho. Okay. the minus sign here didn't come from the denominator, it came from switching the integrals. Now let's do I2. This is this segment here. And now we're going to go basically the same one. Not quite though. The integral from 0 to 1. Here we have just a d rho because z is just rho on this line here. We have the same phase shift. Okay, so you can see that this is the complex conjugate of this. So there's a minus sign here. It's close, but they don't cancel. Now let's do I3. I3, we're going back this way, so it's the integral from 1 to 0, d rho. On I3, we have this phase factor. I'm going to write it as a minus 2 pi I over 3. 1 minus rho cubed to the 1/3 minus rho. Now, if we just switch the limits of integration, we'll get a minus sign here, and we'll get 0 to 1. So these two are the same. I1 and I3 are the same. And now I4, we're going out this way. So this is the integral from 0 to 1. D rho e to the 2 pi I over 3 divided by e to the 4 pi I over 3. 1 minus rho cubed to the 1/3 minus rho e to the 2 pi I over 3. Now let's divide everything by 2 pi I over 3. So this vanishes. This becomes a 2. And this vanishes. So now we get the same thing over here. So our end result is that I equals I1 plus I2 plus I3 plus I4 this is equal to, let's get the plus ones, are I2 and I4. So we're going to get 2 times the integral d rho e to the 2 pi I over 3, 1 minus rho cubed to the 1/3 minus rho. We're going to get 2 times this, and then we're going to subtract 2 times this, which is just the complex conjugate. So that ends up just being, when you go a, z minus z star is equal to 2 times the 2i times the imaginary of z. Okay? So here we already had a factor of 2, so we're going to get 4i times the imaginary part of this integral. That's our final answer. So let me write that again. Make it more readable. It's equal to 4I, the imaginary part, the integral from 0 to 1, d rho e to 2 pi I over 3, 1 minus rho cubed to the 1/3 minus rho. Okay? Now, I'm sure there's a way to do this integral by complex analysis, but since we've already worked a long time on this problem, I just mapled it. And when you maple it, you're going to find that this part over here is just equal to minus pi over 6. I know when you get a nice number like that, there's a way to do it by complex analysis. So our final answer for the contour, the integral over the contour of f of z dz is equal to minus 4 pi I over 6. It's equal to minus 2/3 pi I. And this agrees with what the professor's calculated and what's given as the answer to the problem. So now, in the final video, I just want to show how we could have gotten this nice simple result in about 60 seconds. And it shows that whenever you're given a problem in complex analysis, think a little bit outside the box. Don't just go directly to calculating all these integrals, because that's the whole point of complex analysis, is to use the residue theorem, use Cauchy's theorem to make things easier. So I'll see you in the next video. Bye-bye.